We are now going to talk about a concept very closely related to sequences, that is, series. I've repeated it many times, so I guess you remember it. Sequences and series are not the same, even though in normal use we may interchange the two words. In mathematics, they are not the same. So let's see how we build up a series. Let's say we begin with the sequence an, and we want to see what happens if we sum the terms of the sequence. So a1 plus a2 plus a3 and so on, and we want to keep going forever. So this is not a sum as we know them anymore. This is what we're going to call a series. But how do we formally define it? So we're going to define a new sequence associated to this one that is called the sequence of partial sums. So given one sequence an we start with, we define a new sequence Sn of partial sums in the following way. We are going to see what happens when we just sum the first term, a1, so that will be the first term of our new sequence. Then the second term, we are going to sum a1 and a2. In the next step, we are going to sum a1 plus a2 plus a3, and we continue like this. So the n term of the sum of partial sums is the sum of all the terms of the sequence up to n. So I keep going after a3 and I stop at an. This is a new sequence. So because it's a sequence, we can look at what happens with the limit when n approaches infinity of the new sequence. If this limit exists, so if the limit exists, so we're saying if the sequence of partial sums converges, then this is what we denote by the sum of the sequence from 1 or from 0 to infinity, depending where we start. So this is how we build the infinite sum, by looking at the limit of the sequences of partial sums. There's already one example we have worked with quite a bit, and that's the case where we consider a geometric sequence. So let's say we call it un, and then u1 is the first term, and then the common ratio is r. This is n greater or equal than 1. So we know that in this case, this associated to this sequence, we have an infinite series that for the absolute value of r less than 1 converges. So we can find what the sum of un from n equals 1 to infinity is. And well, it is finite, and actually we can even find it. This is the initial term divided by 1 minus r. Let's see an example. We are going to consider the series associated to the sequence minus 2/3 to the power of n. We want to classify it, so we want to decide whether it converges or not, and if it converges, we want to find its sum. So for this is minus 2/3 to the power of n. This is our sequence un. So that means that the initial term is minus 2/3, and then also is the common ratio is minus 2/3. We need to consider this to the power of n minus 1. So this is our u1, and then here we have r. And it is a geometric sequence. That's why we have tools to classify it and find the sum. And the absolute value of the common ratio is 2/3, which is less than 1. So then we know that the series converges. So we have classified, and now we go ahead to find the sum. We have the formula we have seen for this. When this is going to be the initial term minus 2/3 divided by 1 minus the common ratio. So this is minus 2/3, and I need to multiply it. So this is going to be 1 plus 2/3, so 3/3 plus 2/3, so that's 3 over 5 over here, so this is minus 2 over 5. So the limit as n approaches infinity of the sequence of partial sums, so the series in this case, converges to the value minus 2 over 5. I want to mention one more example of a famous series, and this is the harmonic series. So we begin with the sequence 1 over n, for n greater or equal than 1, and we want to see what happens with the limit of the partial sums of the sequence. So we want to see what happens if we try to sum, take the infinite sum of the terms of the sequence. So we are summing 1 plus 1/2 plus 1/3 and so on. 1n, and we keep going. We can't really prove it at this point. We're gonna be able to prove it later, but actually this series is divergent. But what we're gonna see now is that actually it diverges very slowly. So what we're going to see is we're gonna use our calculator to find what the sum is if we start summing in 1 and we stop in, let's say, 10, or we stop in 100, or we stop in, well, let's see if our calculator can deal also with 1000. And we'll see that the values of those partial sums are increasing very slowly, but actually they are diverging, even if they are doing it very slowly. So let's look at the calculator. So we're gonna use the calculator to find here the sum from, well, I call it n, so from n equals 1 to 10 of the expression 1 over n. Let's get an approximation of that. That's close to 3. We are going to do the sum now, but we are going to sum more terms. We're going to sum up to 100. Let's see. Oh, again, I want to approximate that. So after summing 100 terms, we have a little bit more than 5. Let's see if the software of the calculator can take this. Let's see. Well, let's go slower. Let's sum up to 500 and see what happens. We're not in 7 yet. So let's cross fingers and nothing happens. Don't try it with your calculator at home. It may get stuck, and well, you know, you're gonna need it for the exam. After summing 1000 terms, I'm at 7.49. So this sequence is having a series that it's growing very slow, and yet later on we're going to be proving that it is diverging. So let me just try one more, just because, well, I want to see what happens. After summing 10,000 terms, we're not at 10 yet.